So I just have a short lab here just to demonstrate how some of these particular probabilities works. So first of all, we'll start the classical probability. So for the classical probability now, I say based on equality of an event likely occurring. We have an example here saying supposing a vaccine can either be effective or not effective. So assuming no prior information, both outcomes are equally likely. So we don't have any information, then any of this, we don't have any prior information already. Then these vaccines have equal likely of occurring. So it can either be effective or not effective. So what this means that if we have a sample space, this is our sample space whereby we have head occurring or tail not occurring. So now since these two are likely equal to occur, so that means this will have a probability of 0.5, this will have a probability of 0.5. So you can see what we did in this place. 1 divided by the length of the sample space is 0.5, and we have the length of the sample space. So we're just creating a vector here whereby we're going to be repeating this 1 divided by the length of sample space, which is 0.5 two times. So when we run this, you can see if I should type probability classical now, we already have the probability that is effective and not effective. Now I'm going to run this particular names. So I'm going to assign the names of this particular probability classical. I'm going to give it this particular name of samples. When I call probability classical now, you can see we're already giving name of effective to 0.5, not effective. I've already given names to our vector, so that's what we just did now. So now let's display it. Just what I just showed you earlier on. Now this is it. So that's for the classical probability. I told you that for the empirical probability is based on empirical evidence. So this is evidence we already have, maybe from the past or just like a prior information already. That is the example of the empirical probability. Now let's say we have already simulated a trial. We have empirical probability based on vaccine trial data. So now this time around, now unlike before where we're just using the equality because we have not conducted any trial on that particular vaccine, now we are just simulating a trial data whereby 1,000 patients have received the vaccine. We are going to set seed for reproducibility. So we usually set seed in case we generate random numbers. We're able to generate those particular same random numbers again. For example, that's just an example of why we set seed. In reality now, I just assuming in reality 85% of the vaccine were effective. So based on those particular patients, 85 of the vaccines were effective on the patients, which means that out of that particular 15% was not effective. So now we'll still give the trial size data as 1,000. So now what I'm going to do now, I'm going to create a random vector of 1,000 observations, whereby each of them is stating whether the trial was effective or not, and using the R binom function, whereby out of this particular 1,000, only 0.85 had 1, that is the vaccine was effective, and 0 it was not effective. So I'm just creating a random vector using the R binom function. This is the binomial distribution. So I'm going to be creating a random vector. So I'm going to explain that in the next section about the various distribution. So when I call this effective now, you see I have 1,000 observations whereby 85% of them were successful vaccines, which is denoted by 1. So this is what I just did using R binom. Now I'm going to calculate the empirical probability. I have to find the mean of the effective. So I'm going to call the empirical probability, which is 0.853. You can see that was what we had, the mean of the effective. And if I run this now, so empirical probability of vaccine effectiveness is 0.85. So this mean effective is the empirical probability. What do we just do? We just calculate the number of, because we're probability of effectiveness of the. So since it responded to 85% of the people in the trial, then this means that 85 divided by 1,000, which is going to give us 0.853, is our probability that the vaccine is actually effective, which was what I explained to you earlier on when I was talking about sports and also weather forecasts, when I was giving examples on that. So this is also a typical, this is a clinical example of where empirical probability actually comes into play. Same thing, if I should just change this to, let's say, 100, you can see. If I change it to 1, or let me just change it to 1,500, and I run this together, then you can see now we have 0.8567. So you can see. So and this is just because percentage of the effectiveness of the vaccine on the number of patients trial. So let's visualize the results. So let me just run this again back and visualize the results. We are using for us you are creating a data frame. So let me just copy this. So let's run this. So what I'm going to do now, I'm just going to create the F trial. So what you just did is that we just create a data frame and a single column variable called effectiveness. So those that were effective are signified as effective. Those not effective are signified as not effective. Now I'm going to be using ggplot to plot a bar plot of it. So we plot a bar plot. You can see that those not effective, this is their number at around 850, and those that were effective, you can see around 150. This is it about empirical probability. And I told you for subjective probability is based on a decision or opinion of experts, and this is just an example. So some experts estimate that 70% chance that the vaccine will receive FDA approval. So when you run this, you will just have 0.7. This is just subjective, is just based on decision of experts. It's not something that is a lot of the times we are going to be making use in statistics of that empirical probability. Most of the times is we're going to make use of empirical probability. Here I'm going to be explaining defining events related to vaccine trial. So this is an example now. I'm going to be using this example now to explain events and sample space. The example of this sample space now, we have possible outcomes for a patient in the vaccine trial, and the possible outcomes we have is no side effects, mild side effects, or severe side effects. So this is the possible outcomes that we are having. So now you can see our sample space events are 3, so we cannot have anything exceeding this 3. And probability of having no side effects is 0.75. Probability of mild side effects is 0.2. Probability of severe side effect is probability of severe side effect is 0.05. So now probability events now are going to store it as a vector in the variable probability events. I'm going to give their respective names to this particular vector. So I'm going to be running it so you can see. Then we're going to print it to view what we have. So probability of no side effect is 0.75, mild side effect is 0.20, severe side effect is 0.05. So now I'm going to define these events in various variables A, B, and so now complement of an event. So probability of experiencing any side effects, you can see probability of experiencing any side effects is going to be 1 minus probability of no side effects. So probability of experiencing any side effects is 1 minus probability of no side effect, which I explained earlier on. So when you run this now, you get probability of any side effects, which is 0.25. For joint and conditional probability, let's say we have joint and conditional probability in vaccine trials. So suppose among those who have mild side effects, 40% also experience mild fever. So this is among those who have mild side effects. And we found out the probability of having mild side effects is 0.2. And we now found out that among these particular those with mild side effects, 40% also experience mild fever. So that means we are defining 2 events now: mild side effects and mild fever. So probability of having mild side effects and probability of having mild fever. So this is the joint probability. So, and I told that time that when you have a situation where we're having and probability of A and probability of B, they are going to be using multiplication rule. So because these are what independent events. So the person can have mild side effects and also have mild fever. So we're going to be multiplying that probability, which is 0.2 for mild side effects, with 0.4. And when we do this, we get probability of having mild side effects and mild fever, which is 0.08. Also for conditional probability, probability of experiencing now mild fever, giving the person have mild side effects. So this is a conditional probability. I gave the definition of the formula as this, whereby probability of experiencing a particular event giving another event, then you now take probability of experiencing the 2 events at the same time divided by probability of experiencing the marginal probability, that is the probability of experiencing that event without any condition, which is the marginal probability. So when you now divide this, you get the probability of experiencing that event given that other event. Probability of experiencing mild side effect given the patient has mild fever. Then we have to find the probability of having mild side effects and mild fever. We just got that here, which is 0.08. So this is it. Then we now find this particular marginal probability of having mild side effects. without any conditions attached, which in that side is 0.2. Then we now apply this to our formula. Where is it? We now apply to our formula, which you are seeing here. We run it and we run this. So you can see that conditional probability is what? 0.4. Probability of having mild side or mild fever giving mild side effects. So that is it for the conditional adjoint probability. So now for the addition and multiplication rules, I've already explained a bit about that also. I told that addition rule use addition, subtract from the intersection that is between A and B, event A. And I told you that if they are mutually exclusive, then the intersection is going to be what? 0. So now this is it. Now probability of no side effects. Now we want to find what is the probability of the patient having no side effects or the patient having severe side effects. So you can see that these are two conditions that can occur. If you look at this now, where we defined it earlier on, no side effects and mild side effects, there are two events that can't occur. So which means that the probability of no side effect or severe side effect, we are going to be subtracting it from 0 since they can't occur together. So when we run this now, we have 0.82 probability of having no side effects or severe side effects. Now for the multiplication rule, I thought it's going to be multiplication. That is for the multiplication rule. As you can see, I've already given you the formula earlier. So the probability of having mild side effects and the vaccine is effective. So now this is somehow tricky. Earlier on, we found out of effectiveness of the vaccine to be 0.85 using our empirical probability. And now we know that the probability of mild side effect is 0.2. So now what's the probability of having the vaccine is effective and we have a patient having a mild side effect? So this is where we use our multiplication rule, since they are independent events and these events can occur at the same time, and they can occur at the same time, but they don't have any relationship with each other, because the vaccine effectiveness is related to side effects and the side effect also is not related to the vaccine effectiveness. So because the vaccine might not be effective and have a side effect. So now we are going to multiply these two, empirical probability with the probability of mild side effects, and we get 0.1706 to be the value. So we can also visualize our conditional probability, whereby E is mild fever and D is mild side effects. So we just want to simulate additional data for fever among those with mild side effects. So let's say out of 200 mild side effects, 80 have mild fever. So the number of those with mild side effects is 200 and the number of those with fever is 80. So what I'm now going to do, I'm going to take a probability of those. Now this is now a conditional probability. Probability of those with mild fever giving they have mild side effects, which means it's going to be number of fever divided by number of mild. So because we know that out of those of 200 mild side effects, 80 have mild fever. So that is why we are saying 80 divided by 200. Because we not say 80 divided by the whole number, which is 1000. We are only saying that 80 of those with mild side effects have mild fever. That is why you can see probability of those with mild fever given they have mild side effects is 80 over 200. So then we get the value of 0.4 as our probability. So I'm going to create a data frame now with two columns, side effects and count. So this data frame now is going to be having mild side effect with fever and mild side effect without fever. So let's just call it df conditional. So you can see now we have a simple table here. We have two events, mild side effect with fever, mild side effect without fever. So those with mild side effect with fever are 80. Why those? Because out of 200 of them, they have mild side effects. So but 80 have mild fever. So we subtract 80 from 200, we have 120 of those without mild fever. So this is why we created the table, and we can create a bar plot for this. So you can see it, that these are those with mild side effects with fever and those with mild side effects without fever. So this is it for probability. This is just an intro, and the next section we're going to be talking about the various probability distribution.